On January 30th, 2026, SpaceX filed paperwork with the FCC asking permission to put 1 million data centers in space. 2 months later, a startup called Starcloud raised $170 million at a $1.1 billion valuation. Its first satellite is already in orbit, running an NVIDIA H100. This episode is about a specific argument that has taken hold in 2026. Terrestrial grids are saturated. Compute should leave Earth. The argument is real and well-funded. What we found, looking at the filings and the engineering, is that orbital compute does not solve the concentration problem this series has been tracking across 6 episodes. It moves the concentration upward into a narrower set of hands. The case for putting data centers in space rests on 3 numbers. Solar irradiance in low Earth orbit is roughly 40% higher than on the ground. Solar panels in sun-synchronous orbit can produce nearly continuous power, eliminating most of the battery and backup generation that terrestrial sites need. And the vacuum of space, when used correctly, is a heat sink that water cooling on Earth cannot match. Starcloud projects orbital electricity costs near half a cent per kilowatt-hour. Lone Star Data Holdings, which is targeting lunar storage, projects costs 97% lower than Earth-based alternatives. On paper, a 40-megawatt orbital cluster operated for 10 years would cost about $8 million in energy. The same workload on the ground costs $167 million. Google announced Project Suncatcher in November 2025. The plan is to launch 2 prototype satellites carrying tensor processing units by early 2027. Google's own radiation testing concluded the TPUV-6E can survive 5 years in low Earth orbit. Lab demonstrations hit 1.6 terabits per second on a single optical link. 3 days before SpaceX's January 30th filing, the company completed its merger with xAI. The combined entity is valued at $1.25 trillion. The filing projects that launching 1 million tons of satellites per year would generate 100 gigawatts of AI compute capacity. That number is roughly the entire current U.S. data center fleet. That is the bull case, stated as fairly as the filings allow. The next 8 minutes are an attempt to take it apart, carefully. To see why the orbital case has a problem, it helps to look at the engineering rather than the marketing. The argument that runs through every orbital compute pitch is that you swap one set of physical constraints, terrestrial grid capacity, water cooling, land permitting, for a different set. That is true. The new constraints are just less visible from a press release. Start with cooling. The shorthand says space is cold, so it's a heat sink. The physics says otherwise. Vacuum is an insulator. Heat in space can only leave by radiation, which is far slower than the convection that air-cooled and water-cooled data centers depend on. The International Space Station rejects 70 kilowatts of heat through 422 square meters of radiator. A 1 gigawatt orbital data center, scaled linearly from current ISS-class radiator tech, would need surface roughly 6 square kilometers, over 1,100 football fields. Newer deployable radiator designs improve on that ratio, but not by orders of magnitude. Starcloud's own published design for a 5 gigawatt cluster confirms the math. Their array is 4 kilometers on each side. SpaceX's filing assumes thermal rejection densities roughly twice the industry standard for satellites. Industry analysts, quoted by the Associated Press, said current radiator technology cannot dissipate petaflops of compute in compact form. The thermal wall is the first reason most orbital pitches end up serving inference workloads, not training. The second constraint is hardware aging. Terrestrial data centers swap GPUs continuously as new architectures arrive every 2 or 3 years. An orbital satellite is a sealed system. An H100 launched in 2026 will be 3 or 4 generations behind by 2032. Replacement requires a new launch, a new docking, or a robotic servicing mission that does not yet exist. In April, SpaceX itself filed an S-1 ahead of a possible IPO. Inside the risk factors section, the company disclosed that orbital AI data centers may not be commercially viable. That language appeared in a document filed weeks after Elon Musk publicly called space-based AI a no-brainer. The third constraint is launch. Starcloud's economics assume Starship operations near $500 per kilogram. The grid displacement threshold is closer to $100. Falcon 9 today is roughly $2,700. Johnston, Starcloud's CEO, expects Starship commercial access in 2028 or 2029. Then there is Kessler Syndrome. A peer-reviewed economics paper modeled the timeline. Under historical sectoral growth, a debris cascade in low Earth orbit becomes likely around 2048. Under the growth projections that orbital data center pitches require, that timeline accelerates to 2035. The companies pursuing orbital compute have collectively filed for over 1.14 million satellites in low Earth orbit. The same orbital region the debris models flag as the cascade risk. The series' argument has been that AI inequality lives in the physical layer, the grid, the chips, the inference operations, the data, the rules. Looked at through that frame, orbital compute is not an exit from the physical layer, it is a vertical extension of it. The grid moves up, the chips move up. The rules that govern who can put hardware where move up with them. 3 companies launch nearly all the world's mass to orbit. SpaceX did the majority of it in 2025. Of the entities filing for orbital data center constellations, SpaceX, Starcloud, Google, Blue Origin, Axiom, Sophia Space, Etherflux, China's Ataspace, every one depends on a launch provider that is itself a member of the same concentrated club. On the ground, a country can build a data center in Nairobi if it has the power and the permits. In orbit, a country can host data center satellites only by leasing capacity from one of 6 launch operators. The sovereignty problem this series flagged in Episode 5 doesn't soften when compute moves up. It hardens. The governance instruments that matter for this layer are not the ones AI policy circles tend to track. They are spectrum allocations at the International Telecommunication Union, FCC constellation approvals, and orbital debris liability frameworks at the UN Office for Outer Space Affairs. The decisions are being made now. Return to the filing from the opening. SpaceX asked the FCC for 1 million data center satellites in January. SpaceX warned its own potential investors that orbital data centers may not be commercially viable in April. Both documents are accurate. They describe the same business at the same time. The first is a strategic option. The second is a risk-adjusted disclosure. Orbital compute is real engineering. It will almost certainly work for Earth observation, low-latency telemetry, and a specific class of inference. The economics for general-purpose training, the workloads that actually move the AI frontier, collapse under launch cost, thermal physics, and hardware that ages faster than satellites can be replaced. If the orbital ring gets built at the scale the filings describe, it will not redistribute AI capacity. It will give the entities that already own terrestrial concentration a second tier of concentration, stacked on top of the first. This series has argued that physical concentration is the binding constraint on AI inequality. The orbital chapter does not undo that argument. It extends it into the only layer of the stack that has, until now, been mostly empty.